Next, we have Sreeram Kannan, founder and CEO of Eigenlayer, also known as godfather of restaking. The topic is going to be building hyperscale application on Ethereum. So now let's welcome to stage. Sure.
Thank you so much, Kun. Thanks everybody for showing up. Good morning, everybody. Today I'm going to talk about how we can use EigenDA, Eigen Data Availability, which is a service built on Eigenlayer, to unleash hyperscale applications on Ethereum. A brief intro, I'm Sreeram. I started the Eigenlayer project, a little more than 2 years back, and have been working on blockchain for much longer at the University of Washington, Seattle, where I ran the UW Blockchain Research Lab. Okay, so the title of the talk is Unleashing Hyperscale Applications. So before we go into exactly what I mean by that, first let's look at categorizing applications that exist today in blockchain space across a variety of dimensions. So I'm going to use 2 dimensions to actually characterize the existing applications. One dimension which I think a lot of people think about is throughput, right? What is the rate at which you can run the blockchain? I think there is another dimension which is equally important, which is the first dimension I've listed here, which is value per bit. What is value per bit? So here's the 2 axes, throughput and value per bit. One way to think about value per bit is whenever you're doing a blockchain transaction, you are transacting a certain amount of value. Imagine you're going to Uniswap and paying $100,000 and buying a Bored Ape. Okay, so that's a transaction. That may take 100 bytes or 200 bytes. And in that 200 bytes, you transacted $100,000 worth of value. So it's $100,000 per 100 bytes or $1,000 per byte. That is the value per byte that you're transacting. Okay. So now, when you start to think about applications, you can categorize these applications across these 2 axes, right? What's the value per bit or value per byte that you're transacting, and what's the throughput that you're transacting? Today's applications all sit squarely on the upper left quadrant, where we have very high value per bit, right? High value applications are being transacted, and low throughput, right? So a lot of DeFi, high value NFTs, right? All fed into this use case. But if you look at the fundamental value proposition of the blockchain, it's actually the product of these 2 numbers. Value per bit times bits per second is equal to value per second, right? That's one of the most important metrics. How much value is the blockchain helping to transact? So value per bit times bits per second. The product of these 2 numbers is what is a performance metric of goodness, of utility of the system. Okay, so there is a lot of interesting applications which actually sit on the other side of this quadrant, the bottom right side, high throughput and low value per bit. Imagine a tweet, right? We tweet a lot. Most of it doesn't make any value, right? I mean, hopefully it's useful for somebody, but mostly, maybe I can speak for myself, most of them are useless. So, the product of value per bit, the value per bit is low, but there is a lot of it, and once in a while it's very valuable. So, to unlock, to unleash, that was the title, Unleashing Blockchain Applications or Hyperscale Applications, we need to really figure out how to move blockchains to not only handle the upper left quadrant, which is high value per bit and low throughput, but we have to go to high throughput and low value per bit. Okay, so here's a curve, right? Value per bit times bits per second. If you're the same along this curve, it's the same value per second, so it doesn't, you can go anywhere and still the net utility is the same. But to move from the top left quadrant to the bottom right requires actually several fundamental innovations. It's not as simple as increasing throughput. Why is this? It's because if you're transacting like a $100,000 Bored Ape, it's okay to pay a $50 fee or a $100 fee. But if you are transacting a tweet, right, you cannot pay much. So the cost per bit incurred, the cost basis that you're operating under has to be lower than the value that is being transacted, much lower, right? Otherwise, it's going to be infeasible to use it. So, okay, having stated the problem, so now the problem of enabling hyperscale applications is not simply how we get high throughput, but how we get high throughput and low cost per bit. Okay. So what is leading to the current cost basis in blockchains? Why is it that it's expensive to transact on these blockchains? Let's look at the cost contributors. What makes blockchains expensive to transact on? The first dimension, this took me a long time as an academic to realize, but once I realized it was just staring at my face. Pretty much all the cost on existing blockchains is capital cost. Why is this? If you're staking, right? Let's take one of the most extreme examples, right? Something like Solana. I want to run a Solana network. Maybe it takes several K, maybe 5K, 10K a year to run a Solana node, right? But, and there are maybe 1,000 nodes, right? Or everything's order of magnitude here, just rough numbers. So the total cost of running the Solana network is only a few million, 5 million, 10 million, something like that. But if you had $5 billion staked in the Solana network, right, the opportunity cost of this capital, if you have to pay off for it, we're talking about a 5%, 10% APR. So at $5 billion, a 10% APR is $500 million. So you have to somehow pay the opportunity cost of capital, 10% APR, $500 million. It's insane. So the capital cost is the dominant cost of the cost basis of running a blockchain. Okay, so what other costs exist? That's the operating cost, right? The operating cost is the thing that I want, in the case of Ethereum, there are 500,000 plus validators. These are notional nodes, but the goal is you want to have hundreds of thousands of nodes. In practice, there may be 10,000 nodes if you discount sibling. So they all have to download and run this ledger, execute, download, store a copy, whatever set of operations that are required to maintain a ledger. That's the operating cost. And then there's a third dimension, which is congestion cost. Congestion is the externality that a particular user imposes on other people, right? Because when I'm transacting and I'm taking up the entire block space, other people are getting affected, and you need to pay off for it. So these are the three distinct dimensions to cost. And the weird thing is pretty much all blockchains are pricing only for the third dimension, congestion, right? Look at Ethereum. The price dynamics of Ethereum is basically block space price increases if there is more congestion. If more than half the block max size is filled, then the price increases. That's how the Ethereum 1559 works. Okay, but costs are incurred on all these three dimensions. Capital cost, the cost of staking. Operation cost, the cost of actually running the network. Congestion cost, the cost of externality imposed by your operations. Okay, now we want to, remember the goal, we want to run hyperscale applications. We need to solve the cost basis problem on all these three dimensions. How are we going to do it? How are we going to unleash hyperscale applications in the blockchain world? Number one, to reduce capital cost, we use shared security. This is not a talk on Eigenlayer, so I'm not going deep into this, but the core concept of Eigenlayer is we use the Ethereum stake and the Ethereum stakers and give them an optionality to opt in and run new systems and protocols. Same capital being utilized across a bunch of different protocols. Just to summarize, the high level of staking is you put down some capital and make a commitment that you're going to run the Ethereum protocol correctly. That's what happens in Ethereum staking. What we're talking about is I'm putting down a capital and I'm promising not only that I'm running the Ethereum application correctly, but also this other application, any other application correctly. If I promise that I'm running it correctly, I should run it correctly, otherwise I'm liable to lose my capital. So shared security, or we call it restaking, became very popular as a word, but fundamentally what it is permissionless programmable staking. You're staking in Ethereum. What set of conditions you're binding yourself to is determined by the core protocol. In Eigenlayer, which is permissionless programmable staking, it lets you make arbitrary additional commitments. So that's what Eigenlayer is and restaking is. But fundamentally what it does is it reduces the capital costs because capital is now shared not for one application but across many applications. That's the core idea. So that's how you can actually go make a dent on the capital cost of running these applications. Shared security as a primitive to reduce capital costs. How do we reduce operating costs, right? N nodes, if you want a highly decentralized network, 10,000, 100,000 nodes have to download and store copies of the same data redundantly. Very, very expensive. You don't want to do this. So by building better distributed systems and enabling open innovation on Eigenlayer, anybody can come and build new distributed systems and protocols. They don't have to have a new token, a new system, a new trust network to actually go and launch it. They can come and build on top of an existing trust network, the Ethereum trust network, expanded using Eigenlayer. By building better distributed systems, you can actually reduce operating costs. I'm going to cover how we do it in Eigenlayer later. And finally, congestion costs. Congestion is the result of a common resource, the block space, being near utilization or overutilized or over demand. By increasing the common throughput that is available, you can actually break the cost basis of congestion costs. And you can start doing something really interesting. People talk a lot about the economics of block space and how it's, maybe one of the most important resources in the crypto economy. But nobody talks about cloud space as a dominant constraint in why you can launch cloud applications. If you're willing to pay, Amazon will increase the amount of compute available. That's the natural way in which things operate. So one of the reasons you don't get congestion in something like AWS is you reserve your nodes. A priori, you reserve the number of nodes that you need, so you have them just for you. And it's possible in a plentiful world. In a scarce world, it's not possible. There's not enough to go and reserve something for yourself. By increasing the throughput massively, you can actually create the possibility of reservation. You can reserve, so there is no congestion. Okay, so that's the high level of what is the cost per bit and how we can actually solve the clogging of blockchains to actually unleash hyperscale applications. So I highlighted some of the ideas for how you can actually reduce them, and EigenDA, the Eigen Data Availability Layer, actually takes advantage of all of these things to actually build a system which is very low cost per bit and enables hyperscale applications. Okay, so let's just briefly remind ourselves what the roll-up architecture is. Ethereum pivoted to the roll-up or modular roadmap, which is move computation off-chain, and a single node called a sequencer basically offloads the computation and makes claims about that computation to Ethereum, and Ethereum can now verify the validity of these claims. So when you're offloading computation, one of the important things is you still need to publish the inputs and the outputs of such computation onto Ethereum. So this is called the data availability problem. Why do you need to do this? Why is computation different from data? It's a little bit puzzling when you look at it first time. You're offloading computation. Why not also offload the data? Why not have some other system do the data? The reason that data is different from computation is checking the correctness of computation is temporally non-fluctuating. I take a bunch of code, and then I say, if I run this code, then you'll get this answer. That doesn't change whether it's 2023 or 2030, right? Whichever year we are in, that fact of whether that computation led to that answer remains invariant temporally. Whether I publish the data for somebody else to pick up on is not temporally non-fluctuating. It is very much fluctuating. I may publish a data today and withdraw it tomorrow, or much worse, I may not publish the data now and then later publish it and confuse everybody that the data was always available. So you need to publish the data on a decentralized data layer. That's very, very important in order for the roll-up architecture to work. Okay, and the normal thing people do is to publish it to the Ethereum data availability, and Ethereum data availability is expensive for good reason, because it's fully replicated across these hundreds of thousands of nodes. Okay, so how do we solve this problem? You can solve this problem by constructing a new data availability layer, which has a bunch of properties that will help solve these congestion problems. Okay, so what features do we want from a data availability layer? So just repeating it here, a roll-up architecture is offloading computation, but still needs to publish the inputs or outputs of those computation to a common place where people can download it, because you want to either check the data that the computation has been done correctly, or you want to continue the computation on from the single sequencer. Okay, so what properties do we need? Now, the important problem that this architecture places is all the data of all the rollups have to be published into the data availability layer. So this data availability layer needs to be hyperscale. What do I mean by hyperscale? As you get, more nodes in the system, you need to be more performant. As you get more nodes, the system should become more performant. If you can get this property, then we call this hyperscale. It's, more formally, you would call it exact horizontal scaling. You have n nodes. You have, each node has a certain amount of bandwidth, C. And then the system should be at n times C, right? That would be the theoretical ideal. We're taking a little bit back of NC over 2. Why over 2? Because you want the system to still work even if half the nodes are malicious. So this is the honest bandwidth available, right? So NC over 2. So it's very, very high bar to ask for. So just so we get a sense of numbers in the real world, Ethereum, tens of thousands of nodes, N is either, depending on how you calculate it, you can put 10,000 or 500,000. And each node is required to have 2 Mbps, 2 megabytes per second, something like that. So multiplying something like 500,000 and 2 megabytes per second, we're talking about terabytes per second notional bandwidth available on Ethereum. But the practical data availability rate of Ethereum is 80 kilobytes per second. Just let me repeat it. These numbers don't make any sense, so I'll repeat it again. The bandwidth per node on Ethereum is 2 megabytes per second. There are, 500,000 nodes if you take, every validator as a node. So the total potential bandwidth available is n times C, 500,000 times 2 megabytes per second. It's 1 terabytes per second theoretically available. In practice, we're running at 83 kilobytes per second. Okay, so a hyperscale system will run around 1 terabytes per second or half a terabytes per second. That's pretty insane if you can actually get it. Okay, so when I first observed these numbers, it didn't make any sense that there is 6 orders of magnitude gap between what is theoretically possible and what is practically being done. Okay, but it is true, and I think there's a bunch of reasons for it, but they can all be solved. Okay, low cost. What does low cost mean? When you're thinking about unleashing hyperscale applications, I think the most important thing we talked about is cost per bit. So low cost is, one way of thinking about it is low operating cost. How do we get low operating cost? We get low operating cost if everybody doesn't have to do everything, right? You need to get horizontal scaling. If I have a file size F, I should not require, if there are n nodes, each of them to download the file size F. If I could somehow make sure each node only downloads a little bit, but together they download enough, then you can actually get low cost, low operating cost. How do you get, what are the properties that you may want? You may want low latency. Your rollup is waiting for your data availability layer. You don't want the rollup to be waiting forever. Maybe you want something, what would be the most ambitious is, it should take pretty much the same time that it takes for you to go and write data to Amazon Block Store. 2 times network latency. You send something and then you get it back. Is it possible? That would be awesome. So this is just what we want, right? Verifiable. What we want is not just a system that is working, but it's verifiably working. When I'm seeing the system from the outside, I'm running my phone or wallet or whatever, I should be able to see that the system's working correctly. A lot of the other data availability layers have placed a lot of importance on this property, verifiability. How do you get a light node? How do you get a simple low bandwidth node to check that the system's working correctly? We call this verifiability, another desirable property of a data availability layer. And finally, you want some customizability. Well, you may want to pay in your own token. You may want to do some other things. You don't want a tolerance against 50% adversary. You want a tolerance against 90% adversary, whatever. You may have dimensions of customizability that you want. Okay, so we have designed a system called Eigen Data Availability. It's still not public, so we are still working on it internally. But Eigen Data Availability can achieve all these properties. Theoretically, and practically getting each of these properties to work is going to take time, and there's a roadmap on which we can get each of these properties built. Okay, so the idea is actually relatively very simple. So here is how it works. So you have Ethereum, right? EigenDA is not a new chain. In fact, that's one of the most important innovations. It's not a chain. A chain has the obligation of doing global ordering, right? And a lot of other data availability layers couple the ordering along with data attestations. What we do is instead not decouple the two things. Okay, so how does EigenDA work? Firstly, the set of nodes running EigenDA is basically coming from Ethereum through restaking. Ethereum nodes restake on Eigenlayer, and they opt in to participate to EigenDA. So that's the first thing. So a set of nodes, and when a lot of stake is restaked on Eigenlayer, you start to get somewhat comparable trust guarantees to Ethereum. It can never be identical. There's some good reasons for it, but I won't go into it. But you can start getting something comparable. Okay. What is happening with the rollup is you have the sequencer, and what the sequencer normally does is it orders transactions and updates the state, right? So I'm going to explain how the rollup interacts with EigenDA. So, normally it submits a state root to Ethereum, but while doing it, or before doing it, actually what happens in EigenDA is it takes the blob. Normally it'll write the blob to Ethereum, the data blob, and the commitment on if you run this data blob, what happens to Ethereum, right? The state commitment. Instead, what you do now is take the data blob, okay, and then encode it using an erasure code. Not only you encode it using an erasure code, but also you use KZG polynomial commitments to prove when you're encoding that you've done the encoding correctly. So, I have a data item, and then I'm sending you, I'm splitting it into x1, x2, x3, x4. I give you like x1 plus x3 plus x4. How do you know that I'm actually giving you x1 plus x3 plus x4? I send you a proof, and I'm actually giving you x1 plus x3 plus x4 using KZG polynomial commitments. Okay, so I take the data, split it into chunks, smaller chunks, much smaller chunks. So the original data size is f. When you expand it using this code, it's only 2f totally. So each one is like 2f over n. So each chunk is very, very small if n is large. And you take these chunks and open separate connections to each of these n nodes and send each of them their chunks. Okay? Simple. Take the data, code it, and then send each of the nodes their chunks. Now, each of the nodes receives their data. And remember, they can verify that the data is correct because they have the KZG commitments. They verify that what they're receiving is correct relative to a KZG commitment. Then they sign that they have actually checked the data. They sign it, and then they do like a BLS signature. And they send it back to the sequencer. They check the data and then send it back to the sequencer, which aggregates all of these signatures into an aggregate signature. And now, all you have is the message that, hey, I have received this KZG commitment, and the DA nodes have attested to it. You have an aggregate signature of this. Then you send it to the Ethereum EigenDA contracts. So EigenDA contracts decide on Ethereum. They know who is staked. They know what the quorum threshold is, and the contract can decide that this is a valid data or not. Okay, that's it. So that's all that EigenDA does. This is the fundamental architecture. So take the data, encode it using erasure codes, KZG polynomial commitments, then send it to the EigenDA contracts. No ordering of transactions happen on a DA chain or anything like that. Ethereum is the root, and we are just basically providing data attestations. Okay, so now all the properties that I claimed start to make sense once you see this architecture. Every node's downloading very little, so there is no single node throughput limitation. So it scales linearly. Every node downloads very little, so the cost basis is very low. The nodes are using the same stake from Ethereum, so the capital cost is not significant. And the latency required is, this guy encodes the data, sends it, and then receives it back. It's 2x network latency. Send it, receive it back. Amazing censorship resistance. Why? Normally in consensus protocols, you have a leader, and the leader decides what things go into the protocol. No leader, self-leader, right? So the sequencer becomes the leader, or a notional leader, and it's directly communicating with the end nodes. So nobody, other than a majority of the nodes, can censor this inclusion. So you get, hyperscale. Okay, theoretically, the scale that we can achieve is very, very high. Practically, right now, it's still hyperscale, but far from the theoretical limits. The data rate that we can achieve is 10 megabytes per second, with each node only requiring to download 0.2 megabytes per second, far lower. So it is pretty strong. Oh, I forgot to mention, EigenDA is basically built on the core ideas invented in the Ethereum research community called Danksharding, Dankert-Faced, and Dimitri, and several others, Proto Lambda worked on, like, building some of these earlier versions. And what we've done is taken this core architecture of Danksharding. Ethereum has a roadmap. Right now it's coming up, an upgrade called Proto Danksharding, which uses some aspect of this. But, the data rate of that system will be like 20, 30 kilobytes per second. There is a roadmap on which, Ethereum is going to upgrade to Danksharding, which is 1 megabytes per second. But already we can achieve 10 megabytes per second. So the way this is engineered, okay, I'm not going to go into this because we are running out of time. By looking at all the different ways in which systems are deadlocked and removing all of them is how we achieve this kind of horizontal scaling. There's overheads due to peer-to-peer networking. There is overheads due to upload versus download. There's overheads due to waiting in the heat of consensus. There's overheads due to a single builder having to upload all the data. There's overheads due to encoding. Like, all kinds of things can be completely removed in this architecture. Okay, so let me skip. It's highly customizable because it's a service on top of Eigenlayer. You can run a variant of EigenDA which can do a variety of other things. Okay, I just want to highlight this point, how EigenDA transforms the roll-up economics today. Today roll-ups are only somewhat competitive with layer ones. And this is a huge problem if we envision a world of convergence, where all the different roll-ups are operating on a common trust base so that they can interoperate much more fluidly. But the cost basis today doesn't permit it. So why is this? So the first one is the dominant cost of being a roll-up is actually data availability. And data availability cost is high, right? So on Ethereum. Number two, the data availability cost is uncertain, as opposed to if you're your own layer one, right? It is not at all uncertain. You know how much, normally if you're Solana, you're saying like, okay, I'm taking 3%, 5% of my token emissions and giving it to the validators. It's certain, it's uncertain here. And finally, roll-ups need to pay upfront costs. Another way of thinking about it is roll-ups have exchange rate risk, right? So today you may think like, oh, 10% of my token emissions is enough to like handle a particular, to pay Ethereum. But if your token price goes up or down, the whole thing swings with it. So you're taking exchange rate risk. So whereas with EigenDA, you can actually solve all these different problems. Roll-ups with EigenDA can completely outrun layer ones. First is the DA cost is low, because of the fundamental cost basis I laid out. We also have long-term data reservation, so you can actually reserve data for a whole year. And finally, you can pay data availability fees, potentially in Rollup's native token. This completely transforms the scope of what the Rollup's cost basis is. And they can become very, very competitive with layer ones because you are operating on a shared security substrate, which is actually much cheaper than being your own chain. With that, I'd like to conclude my talk. Thanks so much for listening. A quick question before I wrap up. Oh, yeah, Dalia. Oh, yeah, that's a great question. So how do we ensure... Both great questions. So briefly, we have a mechanism called proof of custody, which actually is used to verify that the nodes are holding onto the data. This is again due to Dankrat Feist and Justin Drake at the Ethereum Foundation, but we've implemented that as the core mechanism for verifying that the nodes continue to hold the data for the period. How do we make sure we handle with churn, right? Nodes coming in and going. EigenDA is a short-term data availability layer. We only guarantee data availability for a week. And by putting frictions on nodes coming in and going out within that week, we can actually give very high guarantees. But this is one of the reasons we don't guarantee long-term data availability. Thank you.